Welcome to the problem-solving session for Chapter 34. Let's begin with the first problem. Here, we are given a sinusoidal electromagnetic wave which has a frequency of 40 megahertz. And recall that mega is e to the 6. This electromagnetic wave is traveling in free space. Well, free space just means vacuum along the x direction. We're asked to determine the wavelength and the period of the wave first. So let's begin in part A. We have the wavelength of the wave is going to be given by the speed of light divided by the frequency of the wave, because of course we have the relationship that C is equal to the product of wavelength times frequency. And here, if we take the speed of light as 2.99 e to the 8 meters per second, divide that by the given frequency, 40 e to the 6 hertz, we get 7.48 meters as the wavelength of this light. And hopefully our calculation is correct. To calculate the time for one cycle to occur, we simply take the relationship that frequency has to period, and that is 1 over the frequency, or 1 over 40 e to the 6 hertz, and that tells us that a very short amount of time passes for one cycle to occur, 2.5 e to the minus 8 seconds. In the second part of this question, we are given the electric field of maximum value equal to 750 newtons per coulomb, and of course that can be written also as, don't forget, the volt per meter, whatever our preference is, and that this electric field is traveling along the positive j hat direction. We're asked to determine the magnetic field of this electromagnetic wave. Well, first let's get the magnitude of this magnetic field using the relationship that electric and magnetic field have for each other. In other words, the electric field equals the speed of light times the magnetic field. To get the magnetic field, we simply divide the electric field by the speed of light, 750 newtons per coulomb, divided by 2.99 e to the 8 meters per second, gives us a magnetic field of 2.51 e to the minus 6 Tesla. And of course, that's the magnitude. Now, to get the direction, we recall that the electric field crossed by the magnetic field gives the direction of the movement of the light. And we were told earlier that the light's traveling in the I hat direction and the electric field was in the j hat direction. So what quantity gives us j hat? So if j hat, what quantity would j hat being crossed by give us I hat? Recall our cyclical permutation. We have I hat cross j hat equals k hat, or j hat cross k hat equals I hat. So the magnetic field is in the positive k hat direction. Next question. Here we're told that television sets, well, these are the televisions of old, used rabbit ears, or therefore antennas, made up of metal rods. And these would be adjusted to be about roughly a quarter of the wavelength of the electromagnetic wave which they were trying to receive. Now, of course, you could always adjust the length of the antenna and the orientation, but let's just say that we are trying to receive light or a radio wave of 60 megahertz. And we're asked to determine the length of each rod, provided that the length is going to be 1/4 of the wavelength of the light. Well, since we're given the frequency of the light, we can calculate, the wavelength of the light using the relationship that the speed of light divided by frequency gives us the wavelength. And 2.99 e to the 8 meters per second divided by 60 e to the 6 hertz gives us a wavelength of 4.98 meters. But of course that would be unreasonable if we had a rod that was that long. So in fact the rabbit ears are 1/4 of that value. So 1/4 of 4.98, 1.25 meters, which is a lot more reasonable in terms of the actual space that we have in our homes using these old television sets. Next question. We are told that we are located 180 meters from a radio transmitter, in other words, from an antenna. And if the radio station which is transmitting the wave calls itself 1150 AM, where AM is in the kilohertz frequency range, the question is, how many wavelengths are we away from the radio station? So how many wavelengths are in 180, so how many wavelengths are in 180 meters? So here, for example, let's first, the first case is the AM, and in the case of the AM, if we take C divided by the 1150 kilohertz frequency, we get a wavelength of 260 meters. So if we are 180 meters from the radio transmitter, that means that the number of wavelengths divided by distance is going to be 260 meters divided by the distance, which means that the wavelength is 1.44 the distance of where we are located. So lambda 1, the wavelength of broadcast, is 1.44 our located distance, and of course our distance, we might say, is the wavelength divided by 1.44. So either way, we can give our location either as a wavelength divided by how many times our distance is, or sorry, that's the first case, or we can give our distance by wavelength divided by 1.44. In the case of FM, lambda 2 here will be equal to C times the frequency of the FM, which is which was given to us as 98.1 e to the 6 hertz, and so the wavelength of that light is 3.04 meters. And here again, we can take that wavelength divided by our distance, 3.04 meters, divided by 180 meters, our distance to the transmission, and we get 0.0169 wavelengths. So what that means is it's about 1.69% the distance where we are located from, the wavelength is to the distance of where we are located. Next question. This one deals with astronomy, and it tells us that the brightest star in the night sky is a star called Sirius in Canis Major, or Big Dog constellation. And we're told that Sirius is at a distance of 8.3 e to the 16 meters from the Earth. The question is, when we look at the star, how far back in time are we seeing it? Well, what we want to know, what we really want to, the way we want to approach this is that we're told the distance is 8.3 e to the 16 meters. Well, we know that from our lecture that 1 light year is going to be given by the speed of light, the speed at which the light travels, times the amount of seconds in 1 year. And what we find out then is that Sirius is at a distance, that the distance that light travels is 9.45 e to the 15 meters. Well, Sirius then is, if we take the distance of Sirius and divide it by 1 light year, we find that 8.3 e to the 16 meters divided by 9.45, sorry, this is 1 light year, 9.45 e to the 15 meters gives us a distance of 8.8 light years away. So Sirius is 8.8 light years away, which means that it takes light 8.8 years to leave Sirius and reach us. And the interesting thing is that when we see Sirius, we see the star as it appeared 8.8 years ago. Next question. Here we are given a dish antenna, which is semi-spherical, of radius 10 meters, and we're told that this dish antenna is meant to capture a sinusoidal wave that has an Emax of 2 e to the minus 5 volts per meter. And we're to assume that all the radiation is absorbed by the antenna. And the first question is, what is the amplitude of the magnetic field? In other words, what is Bmax associated with the electric field that this antenna is capturing? And of course, we know the relationship that Emax divided by the speed of light gives us Bmax. And we plug in our numbers and get a value of Bmax of 6.69 e to the minus 14 Tesla. Next, we're asked to determine the intensity of this light. Well, the intensity of the light is going to be given by the average of the pointing vector, and here we can obtain it by taking the RMS value of the electric field, multiplying it by the RMS value of the magnetic field, divided by mu naught. Well, we've got Emax, we've got Bmax, and we know that these two divided by the square root of 2 will give us ERMS, BRMS divided by mu naught. So we can take Emax here times Bmax. These are both divided by the square root of 2. Well, square root of 2 times square root of 2 is 2. Plugging in our values, we've got 2 e to the minus 5 volts per meter times 6.69 e to the, this is a 9, e to the minus 14 Tesla, divided by 2 times 4 pi e to the minus 7. That gives us a value of 1.67 e to the minus 12 watts per meter squared. And the last question says, what is the power? In other words, what is the rate of energy flow of this light? And recalling the relationship that the average pointing vector has, or the intensity of the light has, to power, it's power divided by area. Here we take that intensity, multiply it by the area, 1.67 e to the minus 12 watts per meter squared, times the area of the dish antenna. Well, it's semi-spherical, and so the area of the hemisphere is going to be 4 pi, well actually it's going to be 2 pi r squared, right, because we have to, it's semispherical. So 2 pi r squared, r was 10 meters. We square that, and we get a value of, let's see, if I'm not mistaken, it's going to be 1.05 e to the minus 9 watts. Next question. We are told that a loop antenna is used as a tuning circuit, an LC tuning circuit, to resonate with a broadcast signal of 88 megahertz. Now in this case the capacitance is not variable, it's constant, but the inductance is variable. If the capacitance is 33 e to the minus 12 farad, what is the inductance necessary to resonate with this frequency of broadcast? Well, we start with the relationship that the resonant frequency is equal to 1 over 2 pi times the square root of L times C. Squaring both sides, we get F squared times F squared is equal to 1 over 4 pi squared times LC. And because we're trying to solve for the inductance L, we are going to cross multiply. So we've got 1 over 4 pi squared times C times the frequency squared, plugging in our numbers. Let's see, 4 pi squared times capacitance was 33 e to the minus 12 farads. The frequency of broadcast 88 e to the 6, that's the megahertz, and we have to square that. We get a value of inductance which is 9.91 e to the minus 8 Henry. Next question. Which of the following electromagnetic spectrum ranges will make the best choice for a telescope that is ground-based? Will it be X-ray? No, because none penetrate the Earth from space. Will it be infrared? No, because only some penetrate. Will it be radio wave? Yes. All radio waves as well as visible rays, visible light, penetrate the Earth's atmosphere. So when we are talking about ground-based telescopes, radio telescopes as well as optical, or in other words visible light telescopes, are desirable on the Earth. So ground-based, visible, and radio. X-ray, gamma ray telescopes have to be put in orbit about the Earth, as well as infrared and ultraviolet telescopes. Well, this concludes the problem-solving session for Chapter 34. Until next time.